What's your last name? Roder. Okay. Anybody there yet? So what's chapter one? Okay, so no, we're not going. We've already gone over that, right? Okay. Huh? Yeah, we had that was the first lecture we had. In fact, we went over it probably more detail than the book actually went over it. Then chapter two. What's chapter two? So we have different types of drawings available. I think we've already looked at a few of them. And mine says chapter four, but it's chapter three in y'all's book. Chapter two. I need to change that. This is the same thing, right? This is a diagram called a pictorial diagram. We talked a little bit about this, right, in this class. So this is most of the time, and this was a pictorial pictures drawing showing the physical detail of components. And this is a pictorial diagram of one of the TVs that I bought. So basically, it just draws what? Pictures of everything. And this is real common with commercial stuff. Where people that don't know symbols and stuff like that, they draw pictures. You'll run into this. So here's some of our symbols. This should be in your textbook. We've already went through this, right? Batteries, thermocouples. Anybody know what a thermocouple is? Nobody knows what a thermocouple is. What is it? That's exactly what it is. So your stove, your oven usually uses thermocouples. These create a voltage that's proportional to the temperature that they're measuring. They're very accurate. The problem is they're not really fast. But these work real well in like ovens and stuff like that because those don't heat up real fast, right? Water heaters sometimes use these. They do use them if you got a gas water heater. They do use the thermocouple to sense when the pilot light is on before it turns on your main gas valve. Then we have photovoltaic cells. You're okay there, right? Or photoconductive cells. Most people call these solar cells. What do these guys do? Nobody knows what a solar cell does. You run into them all the time now. DC, yeah. It absorbs the energy from the sun and converts it into DC for us. And these are the symbols over here, by right. The top, we probably need to know that's an AC voltage source. And then the thermocouple, there's a symbol below that. Photocell, solar cell, or photovoltaic cell. That's given different names. We looked at the conductors, right? Everybody okay there? The symbol that they've got out for a switch is not right. That's a push button. So the switch for these type of switches, they only break one contact. They're not double break contact. They're single break. So the symbol of a single break switch would look like this. So that's the symbol for a single break switch. So notice one side is connected all the time. So if you ever tore a light switch apart, you'd see that one side is connected all the time, and what you're doing is you're switching one side. The symbol of a double break would be the one they've got, where we have two contacts, and then it shows it's setting up like this. So this is a single break, and this would be a double break. And what advantage does a double break have over a single break? Anybody got any idea? Well, the problem is I'm trying to break current. So normally when we break these things, it creates a little arc right there. That arc is basically hotter than the sun, which has a tendency to try to melt metals, right? You understand? So what happens is we get what we call welded contacts. So if you ever seen a light switch that you can't turn the light off anymore, it's because the contacts is welded together. What a double break does, I'll show you a double break contact on a relay. I think I passed it around. So the way it is, it's springed, so it has the ability to tilt. So what that means is, can somebody come up and get this? If one side gets stuck, then it'll tilt, and when it tilts like that, it has a tendency to unbreak the contacts. So double break contacts is more likely not to weld together than single break contacts. So you can push on one side and you'll see the other side tilts up, and so that's the advantage of double breaks. Limit switches, did I show y'all limit switch? Yes, no? Let's see if I can find one over here real quick. So here's light switch. Y'all familiar with these, right? I don't need to pass this around. Yeah. These are single break. So this is a limit switch, and you can actually look in and see when the switches, the contacts actually change. These were given the name because originally they were used just to see when things hit certain limits. We use these a lot now, even to detect when things are at certain positions, but they still have the name limit switch. And you can see this thing's got an operator out on it, and when something solid strikes it, it causes it to knock it down, and of course it's going to cause the contacts inside the limit switch to change states. The symbol for a limit switch, we've got 4 symbols. So we start off by drawing the contacts, and so usually if they're not circled in, it means it's a terminal, which means it's some place that you connect something to, right? Does that make sense? And then we draw the switch, and then we'll draw a little ramp on it, and this would be this is what we call a normally open. Do y'all understand normally open, normally closed? So what does that mean? So right now, when you get that limit switch, it's in a position, right? And if you look at one set of contacts, they're closed, which means they make electrical contact, they allow electrical current to flow through, and then another set is open. And when you change position, the normally closed opened, and the normally opened did what? Closed. Does that make sense? Okay. So this would be a symbol of a normally open, the normally open contact. And then this right here would be the normally closed. So when we look at this, and the way I tell my students to figure this out is what gravity is trying to do. So gravity is trying to open this, so it's already open, so it must be a normally open, right? Gravity is trying to, I drew that wrong. Gravity is trying, I drew a contact, but could hear anything. That's a good question. But let's say I've got a one example was we had a big lathe, a mill machine, and we had a table. We had a table on it. Let me get something to draw. But it could do anything. I've seen them count. I've seen them count things that go by if they're big enough, and it can trigger it. And we do have some very small ones, but it had a big old table, and then the machine set up here, and then what it did, it had limit switches down here. So when this thing moved back and forth, so basically, let me draw it over to this side. So when it came over to this side and the machine was right here, it would hit the limit switch and it would tell it to reverse, and then it would do what? Okay. And then over here it had another limit switch, and then when it hit that side, it would say go back and forth. We've seen them count. This one wouldn't count because it's so hard to trigger. But we'll look at some small. Well, they have a whip sitting out there instead of having that, and something goes by, it just knocks it out of the way. And when it knocks it out of the way, it counts things, you know. So they like I said originally, and this is why they got the name, is this is what they were used for. They were used to detect when something hit its what? Limits. So it got the name limit switch. But we use them for all kinds of things. I mean, all kinds of things. Counting, I've seen them used for counting. I've seen them used when something's at a certain position to stop, not when it's at a limit, just when it's what? At a certain spot that we don't want it to be at. The only problem we have with these, of course, these are electromechanical devices. They're very rugged. They can run loads, which means they can handle a lot of current. They can handle a lot of power, depending on what size you get. So I've seen motors run off these things instead of picking up relays. The only problem we have is they're electromechanical, which means there's two things. It can fail two different ways. It could fail what? Your car is an electromechanical device, which means what? It can fail electrically or it can fail mechanically. So these things, and then plus they got to be adjusted. If they don't adjust them right, they're mechanical. So what happens is they get them up too high, and the big thing comes back and knocks them off and stuff like that. And plus, a lot of times the guys will open this up when they're troubleshooting, so it's all sealed up and got gaskets in it. And then when they get through, they leave the cover off because it's an inconvenience. And then garbage in industry gets inside there and causes the contacts to go bad. So a lot of things is just people not sealing them up the way they're supposed to be sealed up. Like motors, I've seen DC motors where it's inconvenience for them to pop the cover off to clean the commutator, so they just leave it off, and eventually it burns the motor up because garbage gets in there. So a lot of things where these electromechanical devices go bad, you can't blame it on the device, you blame it on the people that are lazy. So this is actually a normally closed contact. I didn't touch. It's got a touch. So gravity is trying to close this one, so it's closed. Now, why we have different symbols is we're going to come up and if we're going to stop this piece of equipment and it's sitting like this, and that's its normal position. That's where it's sitting at every day when I come into work, right? You understand? Well, even though this is a normally open contact, in the machine's normal position, that contact would be held closed. So that's why on limit switches we have two more symbols. So notice on this one, so this one right here, notice it's drawn below. So gravity is trying to open it, so it must be what? It must be normally open, held closed. That makes sense? Y'all understand that? Now this one, if I come over here and look at this one, I'm going to draw it above. Gravity's trying to close it, so it must be what? Normally closed, held open. What we're doing is we're looking what gravity's trying to do. Y'all understand? And this is a little... It's normally open, but it's being held closed by the equipment. So we name these things when I turn the equipment off at night. Usually we start these things from a certain spot. Well, a normally open contact, if you turn the machine off or park it, then it's up against that thing, and so if it's normally open, it's going to be what? It's going to be held closed, right? You understand? So like this one right here. So this is a normally open contact, and this is where I park my machine every night. This is a normally open contact, but the machine when I park it is holding it closed, right? You understand? So what we do is we look and see what gravity's trying to do. So I come over here and do this. What's gravity trying to do? Trying to open it. Well, it's open, right? You understand? Because it's below this thing right here. But if I take this same symbol and draw it below, notice it's going below, okay? So gravity is trying to do what? Gravity is trying to open it, so it must be held closed. That makes sense? So if I come over here and draw it this way, this goes on the top. Gravity's trying to close it, right, to come to rest on this guy right here. So if I come over here and draw that like this, gravity's trying to close it, so it must be what? Must be normally closed, held open. That makes sense? So limit switches, this is why we have 4 different symbols, because we draw the symbol on what the state of the limit switch is when the machine's at its park position. Are we okay? Foot switches, anybody seen a foot switch? So this is a foot switch that you do what? Activate with your foot. And these are disconnects. These are mechanical disconnects. So a disconnect, a mechanical disconnect, it usually uses something called a knife switch. So this is a disconnect, and of course the handle's not on it to prevent somebody from just moving it. So this is a disconnect. I guess I should be showing this on the camera since we got a few people that's not here. Did I bring up my camera? I don't think I did. Relay, is it next? Hopefully. So I don't see it, guys. It's probably there, but I just don't see it. So a circle with 2 connection points coming out of it is the symbol of a relay coil. And a relay coil controls contacts. Oops, sorry. Supposed to be a nice circle. And then if I take the same symbol and put this, that turns it into what? A symbol for a light. Thank you. So what we do, this shows a diagram for a waffle iron. And so this is the actual item, and then this right here would be the actual diagram. So the heaters is drawn as resistors. That's all electric heaters. The elements of electric heaters, that's all they are. They're resistors. And then when you put current resistors, they have a function in life, but everybody in here has had DC, right? We have that. And what did the resistors do in your circuits? They did one thing. What was the power? When we created power, what was it? Came out in the form of heat. Yeah. So all of these are just wires. They don't use copper. They usually use like tungsten and stuff like that. It has a lot more resistance to it. They put current through it and it gets hot enough to turn red. That's what an incandescent light bulb is. It's nothing but a resistor. It gets hot enough that it burns light or displays light. Of course, we have to put that in a vacuum because it was an oxygen. It would actually disintegrate. Right? So this is a symbol for. I need to do this. This one right here. So I'll draw it out here. So it's this, which means it's it's this, which means it's normally closed. And then it's got these crooked lines like that. It's not in these groups. It looks like some of the slides are missing here. This is a thermal switch. I told y'all where all the symbols were in the back of y'all's book, right, in the appendix back here. This is a symbol for a what? No, it's not a relay. When we come over and see this, this is not a limit switch. So those only come into play. This is a single post, single throw, just switch, right? Okay. And of course, what's this a symbol for? Resistor. So what happens? We close this up. These things come up and start heating up. The thermal switch is normally closed, and then when it gets up to a certain temperature, it does what? Opens and turns the heater off. And then when it cools down to a certain temperature, it does what? Closes back. The float switch or liquid level switch would be drawn like this. It would have a, and then a pressure switch would be half of that. Okay. And then of course the limit switch is it's the one that falls into the rule of this thing right here. It has the little ramp on it, right? It shows what, basically it's trying to show what the device runs up against when it changes the direction. Are we okay? This is this is a diagram using electrical symbols. This is actually the diagram that was on in my HVAC system. Or is this in the book? I don't think it is. I think I got this off. Huh? Yeah, I didn't think so. I thought I got this one off my HVAC system. It's been quite a while. Notice these are all different devices, right? And what we have to understand is that this looks like it's a wiring diagram, and we'll talk about the difference. A wiring diagram tries to show how things are associated with each other. So when I come over and see these little dashed lines around it, it means all this is inside one unit. Where a schematic don't care. A schematic draws things according to logic, how it works, and it don't try to give you an idea of what's inside the same units, right? Does that make sense? Oh, that's the one we already seen, right? Yeah, so this would be, we call this a wiring diagram. So what it's telling us is these devices right here are what? All in the same enclosure, right? And then a schematic diagram doesn't not show y'all, it's going to try to show you the logic operation of the circuit. No, it's just an enclosure. Yeah, it's just a box. So this would be like your relay module that's out there under your car. It's all inside of what? A box. So a wire diagram would try to draw everything there together and do what? Put it inside the box. Or a schematic would draw it the way it operates, right? You understand it? And this gets you to, you'll see students do this, especially in DC. We'll get a parallel circuit and they'll try to wire it exactly the way it's drawn. In real life, they don't do that. They wire things and they try to run things so it uses the less wire as possible, and they have no crossing wires. So you think about a printed circuit board, all the conductors cannot cross each other. So that means when I start numbering these things, usually they'll start in the left-hand corner and go R1, R2, R3. When you look at the schematic, R1 and R23 are going to be drawn right beside each other because that's the way they work. It's not how they're located, it's how they work. So we have a problem is that people waste a lot of wire because they try to wire it the way it's drawn, right? You understand? And so instead of the way it should be, the way it would be wired in real life to use the minimum amount of wire I can possibly use, right? You understand that? Does that make sense? Y'all gonna do it in here. We're gonna draw L1, and somebody in here is gonna try to connect everything back up to the transformer instead of jumping it out in the circuit. And the analogy I use is that when you open up your breaker box or your panel box, anybody ever pull the cover off the panel box? And how many wires go to the breaker? One. If it's more than one, you got a problem. You got an electrician that you should never call back. But it has one because all the jumping in the parallel circuit is done what? Inside your walls, at the outs, and stuff like that. And you'll very seldom see power sources with more than one wire hooked up to each terminal. But yeah, we'll do that here. We'll have people that come down like this, and we'll have a connection right there and connection right there, and they'll jump it. And these two guys are this far apart, but the way it's drawn, they'll bring one. They'll come up here, and they'll put a common spot over here, and they'll come down here and put the other one right there because that's the way it's drawn. Instead of realizing the things are what? They're right beside each other. So instead of using all this wire, and somebody in this class is going to do it, I'll bring it to your attention too. Yeah, but they could have come over here and did what? They could have done the jump right there. But they think because it's drawn that way, they're going to do what? So they'll have L2, and they'll say, I'm going to run L2, and they'll just start jumping, and they'll be from here, and the two sides next together. So they're over here separated, like one's down here and one's up here, but they think they got to go way back up here when they're up there they're beside each other, just because it's what? Drawn that way. So circuits or schematics or diagrams are trying to show how the circuit logically works. It makes it easier to troubleshoot. It's not how they're wired. It's just easier to understand how they work, right? You understand that? Yeah, somebody's going to do that. And I said, these guys are right beside each other. Follow these wires. This goes here, and this goes lit up here, and they're right beside each other. This is a schematic. This is, I don't know where I got this at. This is a 1,000-watt RMS power amplifier. And it uses symbols. If this thing was trying to draw with a pictorial diagram, it would be almost impossible. If it was trying to draw as a wiring diagram where you try to show the orientation of everything, how it's actually mounted and stuff, it would be almost impossible. But this guy right here is not drawn according to that. It's drawn to show me how it works. I know the input is here, and I know the output is here. Right? You understand? So schematics in the U.S. are drawn from left to right. Your inputs are on the left. Your outputs are on the right. No matter how it's connected on the circuit card, right? So the circuit card, what the engineer is trying to do is trying to get everything oriented so we don't have any crossing lines, right? You understand that? And then plus to make the shortest path to get to the between is possible. And y'all know what a printed circuit board is, right? I'll see if I can find one. I'll try to find a motherboard for a computer and let y'all look at those things. And this is just one channel too, guys. This is so people understand why we need plus and minus power supplies. Well, this guy works off of AC. These guys work off of DC. So notice down here we have a minus 70 volts DC. Up there we have a plus 74 volts DC. These guys turn on right here to generate the bottom part of the alternation or the sound wave, these turn off, and then those conduct the top. So this is why we need plus and minus power. So inside your radio, somehow they're taking 12 volts DC and converting it into a plus and minus DC. But they're doing it electronically, right? Line diagrams, also referred to ladder diagrams. Sensors interconnected by lines, and this is what we're going to do. This is motor controls right here. So motor controls, the diagrams are given in what we call line diagrams or ladder diagrams. And you can see why it's called a watt. Why is it called a ladder diagram? Because it looks like a watt, a ladder. And each individual circuit that runs between L1, so L1 is considered to be your hot side. L2 is considered to be the neutral or the common side, right? And then we draw our circuits between L1 and L2. And each individual circuit is referred to as a rung. This is a magnetic motor starter, and I know it's a motor starter because it has overloads. Did we talk about that in this class? Okay. So what's the function of the overloads? So this motor here, where's the stator at? This is a little single phase motor, and I can't put my camera up, so I just have to pass it around. This is the stator, and this little red thing right here is the overload. It's single phase, so all we have to do is just break one side. So a lot of your small motors don't have external overloads on them. They have internal overloads. You'll see it, and it's a little thermal switch. And this gets dangerous because what happens, this came off an HVA system, and your blower starts running. The electrician goes out there, the HVA system tears it apart and gets his arms in there and don't disconnect power, and then these guys automatically reset, and he's got his hand inside the blower, right, and all of a sudden it does what? Cuts on. But most of your small motors have internal overloads, especially just about every one that you got to get your house. So pass this around again. Big multi-voltage motors in the industry, a lot of your motors have the ability to be wired to run off different voltages. And why? Because most industry has multiple voltages there. Now, if available where you're at, which would they do? Would they wire it for high voltage or would they wire it for low voltage? Why? It takes less amperes to run the motor, which means they can run smaller gauge wire out there. But what you do is you literally rewire the motor. So you have a little box on the side of it, you take it apart and rewire it. Well, the overload sense a current. Well, if you wire for high voltage, it would pull less current. If you wire it for low voltage, it would pull more. So you have to have the ability to set the overloads or change the overloads to match the motor. So all your dual voltage motors will have external overloads. Your single voltage motors will probably have internal overloads. That makes sense. So dual voltage motors, I've never seen run more than 2 voltage. Ours is a dual voltage motor. And so I will show you all the overloads. This is the actual circuit hooked up here, by the way. So what happens is we come over here, and this is probably, I think I told y'all, this is the most common circuit used in electrical controls. We have a normally closed stop button. We have a normally open start button. And so what happens is we have our voltage sitting right there. Nothing's going to drop any voltage, right, because there's no resistance there, no current flow. We give every relay a name. If it fits in there, normally it don't, but it'll be around the relay somewhere. They're calling this relay M. They're giving it a name. And then the contacts that are controlled by that relay, they give those contacts the same name. So it means this contact is being controlled by that relay. Down here I see another M, so that means this contact is being controlled by that relay. Everybody understand? This is a normally open contact. Normally open means if the relay is not energized, that contact will be open. This is the symbol for a normally closed contact, which means if the relay is not energized, this contact will be closed. So as soon as I put power across L1 and L2, the light is going to come on. Everybody understand that? That makes sense? Now I come over here and press this button. I don't have to hold it down, because as soon as I press that button, then all of a sudden this contact closes. This guy right here closes. This guy right here opens, right? The light should go off. Then I let go of the start button. Then we pick up this secondary path that keeps current going to the relay coil. So it locks itself in, right? Understand that. This is called a three-wire circuit. And why it's called a three-wire circuit is because it has three wire numbers between L1. This is wire number 1, wire number 2, wire number 3. These are considered the same wire because they are electrically exactly the same, right? You understand? People call this a three-wire circuit because there's three wire numbers between L1 and the relay. It's also called a sealed-in circuit because it does what? It seals itself in, and some people call it a memory circuit. But this is a standard, what we call a start-stop circuit. How do I stop this thing? What's this running? Stop button. Now this is the control circuit. We also have what we refer to as a power circuit, which we don't see. So the actual power circuit would look like this, where I'm going to take three-phase L1, three-phase L2, and three-phase L3. This is single phase. We go through a transformer. So actually the way our circuit is wired is we have a step-down transformer right here. And then we come over here and we go through this. This is going to be labeled M. We'll come over here. This is going to be labeled M. We'll come over here. This is going to be labeled M. Come down through here. These are the overload sensors. So these are the guys that's actually sensing the overload to cause these contacts to open. And then we'll come down here and we'll put the symbol for our motor. It's a three-phase motor. Technically on the relay, this would be called L1, this would be called L2, and this would be called T1, T2, and T3. So you're supposed to input on the relay on the L's and outputs on the T's. So basically most control circuits are made of two circuits. So we have the what? The control circuit that just shows what's controlling things. And then we have the power circuit, which is actually where the power is involved. Now, why we like to do that, it allows us to actually break these up, right? So we'll have one cabinet that's low voltage that everybody has a key to, and then you'll have one cabinet that's high voltage that probably takes 2 or 3 keys to get into. Getting inside the higher voltage cabinet will kill you if you mess up. Getting inside the low voltage cabinet will probably hurt you. Some of them can kill you, but it has a lot less chance of doing that, right? Okay, so let's come up here and look at the circuit. This is, I'll give you all a copy of this. I know you can't see it. This is actually a true diagram. This came off of, we did a training session for, they tried to do a training session out at U.S. Steel for their electronic repairmen. And they put them up at the training session for a year, and they did everything on computers. So it was all online, basically, but they had to come in. And then when they got time of the year and they had to pass the test, I think only 2 people out of the whole group passed the test. So they decided to send their guys out here for a month, 4 weeks. So we did the training. They did it in a year and 4 weeks. And paid the guys full salary while I was out here. And we had 18 people in class. And when they graduated, 16 passed the test. 2 didn't take it. One guy realized that he was making more money as an operator than he would make as a technician. And the other was a lady that had a baby, so she couldn't take the test. But so that's why U.S. Steel, they make it a lot harder now, but U.S. Steel used to pay for their tuition from the come out here. So this is actually the print off of a number 4 galvanizer line, the actual electrical control. And we'll be looking at this a lot because this is industry standard right here, how this thing is labeled and how it's nomenclatured and everything is industry standard. The book does a really good job of teaching this. And we'll start off after a while when you have to draw these things, you're going to have to use your industry standard to number them and stuff like that. Got a lot of information up there, right? But you'll learn everything up there. This is called a one-line diagram. This gives people problems sometimes. Everybody knows in electricity that every load has to be connected to 2 wires somehow, right? We know that. So why draw the common if you know it? And you'll run into this if you take digital. And this gives us problems too in that class. In a digital schematic, they don't draw the power to the integrated circuits because they take for granted if you got enough sense to be in there, you know that it's got to have watt to it. And every wire they leave off, the easier it is to draw, right, or easier to understand. It's not as common. That's why they came up with a symbol for common. And this gives us problems too. I've heard this 100 times. Well, I thought that was inside the trainer. When they see one of these symbols, like when they see this symbol here, and then over here they see this symbol somewhere, and they say, well, I thought it was in the trainer. No, it's not in the trainer. It's the symbol of a wire. You have to do what? You have to run the wire between all those symbols. But using that symbol, we decreased what? We decreased the whole schematic by 1 wire, which makes it a lot easier to understand, right? So this was probably, that's the symbol for a ground, by the way. This is the true symbol for a common, which you won't see used a lot. It's without the dash. So if you ever see this symbol, this is still the same thing. You still got to run the wire. But what that symbol means is that it is not referenced to ground. If you see the little 3 dash lines, it's supposed to mean it's referenced to earth ground. And but that's one of the most misused symbols in the trade, right? You know your car does not have an earth ground on it, right? But just about every diagram you see for a car, guess what they use for a common? The little 3 dash lines. Even on integrated circuits, integrated circuits from manufacturers like Texas Instruments will label the common pin ground. So these are big guys too. So signal line diagrams, what do they leave off? They leave off the common because they take for granted you what? You know it's got to be there, yeah. One line diagram is that use a single line graphic symbols to indicate, and it leaves off the ground, right, or the common. You need to learn these electrical symbols. Where are the electrical symbols in your textbook? Back in the appendix. So, if you don't know the symbols of your trade, what can't you do? Can't work in the trade, exactly. You can't read the diagrams that they give you out. Right? They just don't make any sense. Oh, we've already talked about this. Everybody okay on these? Normally open, and this is the only place this is going to come into play is on limit switch. These normally open, held opens, and normally open, normally closed, normally closed, held open, and normally open, held closed. These are where these symbols will come into play. Put switches, limit switches, and other switches, we don't have that problem. Which gets confusing because on a single pole, we draw it open, normally open position on the top, right? You understand? On the limit switch, it's drawn according to what gravity's trying to do to it, which confuses some people. Electrical schematics circuits include, of course, the source. What's that a symbol for? Yeah, it's a DC voltage source, right? It's probably a battery, but each one of these lines is supposed to indicate a cell. But most people don't understand it too. So this would be a 3-cell. Your car actually has 12 cells in it. I mean, I'm sorry, 6 cells. So this is a dual voltage transformer. We looked at that a little bit, right? Everybody understand? Wired for high voltage because the primary coils are hooked in series. This would be considered L1. This would be considered L2. And I need to do this, guys, because I'm recording this. Now this would be L1. This would be considered L2, right? If you're going to reference a line to ground, L2 would be the line that you would reference to earth ground, right? And then we draw. This would be a rung. And this is the same diagram with pictorial. Pictorial would be easier for you to hook up because you wouldn't have to know that this represents that, and you wouldn't have to know this represents that. But so pictorial diagrams are for people that don't know symbols, right? So like I said, most of the stuff you buy commercially, like TVs and DVD players or stuff like that, they'll use pictorial drawings because the people that connect them up don't know symbols. So these are just some more circuits. We do have basically switch with an overload on it here somewhere. I'd have to find it. So motors usually require overloads. Some of the overloads can be internal. Sometimes they're not, right? So just about all the motors in your house. Where do we have motors at in our house? Air conditioning, right? Probably if you got probably more than one on your air conditioning system, it's got an outside unit, right? Where else? 7 fans. Some people don't have 7 fans, but okay. Doorbell's not a motor. Doorbell is just a relay, and it's real easy. Now doorbells are electronic, but in the old days it was just a relay, and this was a normally closed contact, and then they had this, and then the relay actually mechanically just operated a knocker. So what would happen is every time the relay would energize, it would open the contact, it would drop out, then it would just sit there and vibrate. Somebody's going to do that in this class, by the way, not on purpose. Especially when we get into reversers, then you got to connect 2 relays together, and you got to monitor them. Somebody in this class is going to hook it up backwards, and as soon as they hit the start, it's going to go brrr, and it's going to be just like an old doorbell. Washing machines have motors in them. Dishwashers have motors in them. Dryers have motors in them. If you got any type of fan you have in your house, some people have the vents at the top of the house actually have fans in them. And those are all single-phase motors. Every one of those, I've never seen one that has an external overload on those. They're all used internal, just like the one I showed you. So these are just diagrams, guys. They're showing pictorial diagrams. Float switch, right? A switch with an overload in it. And this would actually be the physical appearance of a float switch. And they're using it as a sump pump in a basement. Swimming pool. We used to have a swimming pool, but we didn't have one of these. So on this one, they have a float switch. So if the water level gets down at a certain level, what do? Oh, it's a livestock water. It's not a swimming pool. It would automatically do what? Fill it back up to a certain level. Yeah, we always had to put water in ours. Solenoid. Everybody understand a solenoid? So what's a solenoid? That's a symbol. A lot of times when I throw that symbol up there, they say, well, "What's the symbol?" It's a resistor. But a resistor has like 5 of those, right? And then a solenoid it only has what? 2. What does the solenoid do for us? Yeah, it's actually electrical. Electronic is usually something that's controlled by a solid state device. When we start adding solid state devices, but yeah, this is just electrical. And even in our, we run into a lot of these. Unfortunately, they can't lock and unlock your car doors. And why is that? These only create force in one direction. If we're gonna make them go back to their at-rest position, we got to either use a spring or we got to use gravity. Okay. So on your door lock, it's actually a little motor that you hit. It runs one way and hits a limit switch, right? Which causes it to do what? Stop when your motor's up. Then it spins the other way and hits another limit switch that stops when the motor's all the way down. And now it's got the windows are very, very smart now. They actually detect if something gets in their way. And that's one of the things that Brose does. They do the electronics that actually runs the windows. They build the window frames, and they build they do the seat frames too, with all the stuff that's in our seats now. We have heated seats now. We have lumbar on there. We can change the tilt. We can change the forward. We can do the backrest. And they do the actual frames and all the electronics inside that runs our seats now. Cars are amazing. Used to, of course, we just had a distributor out there that controlled the firing of the angles, and we'd have to time the cars and everything. Seats were mechanically adjusted. Now, then they went to an engine control module. Now they got at least 2 computers in there. They got an engine control module and a body control module. So you got a computer that just runs what? The body, and you got a computer that runs the engine. I think that said one was talking to him, like one of the Teslas like had 7 computers inside the thing. These are just examples showing a line diagram, or these are called line diagrams or ladder diagrams. We'll go between the two. I'll use both terms myself. This shows the makeup of a relay. So all a relay is a solenoid that we've connected what to it? Contacts. And what's nice about these is the power that's running the coil does not have to be the same as the power running the contacts that goes to the contacts. It's just like you in the light switch. You're not electric, right? So the power you use to turn the lights off and on is totally isolated from the contacts that's controlled in turning the lights on. So the coil could be DC, and the contacts could be controlled in AC. The coil could be AC, and the contacts could be controlled in DC. By the way, a relay that's designed to run on AC, if you ran it on DC, it would burn up because the AC depends on a little thing we touched on a little bit, that thing called inductive reactance, which is so inductors change, set in opposition depending on the number of turns and everything. Everything in AC relay that's designed for AC and put it on DC, you're going to have almost a short circuit. If you take a DC, the DC gets its resistance from a lot of wire. So if you take a DC relay and try to energize it with AC, it won't work because it'll have so much inductance reactance, you'll never want to put in another current. So when you buy coils, you have to buy either AC coils or DC coils, and it's rated at the voltage and the frequency that the coils are designed to run at. So if you look at this coil right here, it says it's 120 volts, 60 hertz. So if you put it on 240, what would happen? It'd burn up, yeah, because it's going to try to pull 4 times the power, right? hopefully I got this in this slide. I don't know. So normally in controls, we have two circuits. We have the control circuit, and then we have the power circuit. This is usually drawn as a wiring diagram, which is very, very complicated because what they do is they draw the control circuit along with the power circuit. But this is the actual power circuit right here. So we come through. There's contacts. What's it being controlled by? It's being controlled by that relay right there. It has the same name, right? And this is a double break contact. So we want to make sure this load goes off. And then here's the actual control circuit. So what a wiring diagram attempts to do is try to draw the circuit where things are in relation with each other. So here's the control circuit, which we usually totally ignore because this guy right here makes it easier to understand, right? So normally your power circuit is a wiring diagram. The difference between a wiring diagram and a ladder or schematic or ladder diagram, the ladder diagram shows you the logic of the circuit, how it works. This guy tries to show how things are oriented or physically oriented in relation to each other. And when we get into ours and start hooking up the motor, we will see both of these. But on this side, we're concerned with that one. On this side, we're going to ignore the control circuit, and we're just going to pay attention on how we need to wire the motor, right? You understand? Because they're isolated from each other anyway. Questions on that? So normally control circuit is two parts. It's a what? It's control circuit. Control circuit's usually low voltage. And then your power circuit would be high voltage. What advantage does low voltage have over high voltage? It's safer for me. The control's the same. We use relays, we use switches, we use, I can get contacts. And so the advantage of low voltage is nothing but safer. What advantage is high voltage? Less current to produce the power, which means I can use smaller wires. I can use smaller fuses, right? You understand? So high voltage is not more efficient. High voltage is cheaper to install, and it allows us to run smaller conductors, which means they're even easier to manage. So that means right now, if your water heater, it's an electric water heater, if it was running off 120, the conductors going out there would have to be at least twice the size, which means now they could not run them through the wall anymore, right, to understand. And they would be a lot harder to handle, right? They would not be as flexible. Using house wiring, we don't use stranded wire. We usually use what we call solid strand wire. And what advantage does solid strand wire have over stranded wire? It's a lot cheaper because to take the strands, and you already see the equipment that makes stranded wires, but it's easier to terminate. So solid strand wires, we can just wrap it around a screw and tighten it down. Or we can take it and twist it together and put a wire nut around it. We can't do that with stranded wire. Stranded wire wants to do what we call bird cage. So if you put it under a screw and you tighten it out, it would try to spread out. And as soon as it does that, if one strand comes out from under that screw, then you change the gauge of the wire. So stranded wire, we usually have to put terminals on, crimp terminals, or we have to put them in compression screws where we have a trough we put them in and don't let the strands do what? Separate. What advantage is stranded wire? Got one advantage. It's easier to run because it's flexible. Stranded wire is flexible. It's real easy to run. It's real easy to pull. Right? You understand that. But it's harder to terminate. The advantage of solid wire is that you can terminate it or splice it. How does the electrician splice? They just take two wires and do what? Twist them together. Got what we call a wire nut, which does what? Just screws down on the top of it. So couldn't do that. Well, you could if it was stranded. Normally, if we did that, we would solder them together because eventually the so you need to know this. Advantage of low voltage. This is why our control voltage is usually a lower voltage. We're using an industry standard that's been around. Even today, they're dropping the control voltages to around 26 volts. Not the power, the what? The control. So this is why we got to wear a little more PPE here, because we're up above the lethal levels for voltage, 120 volts. We've already looked in the ceiling circuit. You understand that? Pretty neat, right? Like I said, that's probably the most used circuit because I can put a push button out there instead of a switch. A person can go out there with a glove on and just hit it once and start it, right? You understand? And then hit another one and do what? Stop it. But look at the control circuit. So if you trace this out, guys, you would find out that these two circuits are exactly the same. But in a wiring diagram, we try to draw the circuit how things are related to each other. So what that tells me is the start and stop button are inside the same enclosure, and you can actually see it up there, right? So if I look at this, I know I would be looking for a box and not just a push button. So there's our start button, and then it comes over here. Here's our seal in that's in parallel with that. Here's the actual relay coil, which is located here on the phase, and this goes back. Now here's the circuit up here drawn using a ladder diagram, which is easier to understand. Hopefully that one to you. And so this is the big difference between a wiring diagram and a ladder or line diagram. Line diagram is not trying to show you how things are oriented with each other. It's not trying to show you what's inside the same enclosure. It's trying to show you how the thing works. And like I said, when we get into these, normally all we use them for is what? How do I hook up that motor to this relay right here? So this motor must have internal overloads, because what's missing over here? We don't have an overload contact right there. So this motor would have internal overloads. And it would use a relay that we call a contactor. So a contactor is designed to handle heavy loads, but it don't have overloads. A magnetic motor starter is designed to run motors that don't have overloads, right? That makes sense. So that would be a contactor. And then we'll have another category that we call a control relay that we'll talk about here in a minute. Guys, I try to give y'all a break about every hour, but when I get started, I go. So what y'all need to do, so we've been gone an hour and a half. So what y'all need to do is when it's around an hour, somebody needs to do what? Yeah, somebody said my class before, they understand that. I won't stop at that instant. I'll try to get through my train of thought, but we'll have an hour. We need to do that because this class, is quite a long class. It's not like an English class or something like that where you're in there for an hour and a half and then you go, right? We're in many term classes, so the class is supposed to be 5 hours a class. So we're going to take a 10-minute break. Even if you're not going to take a break, what you need to do? You need to get up and if you're absent, I had already called roll, so if you came in late, you need to let me know you're here. Let me load up the software first, though. I know it's already logged me out. So. Oops. You're supposed to turn off cold this week. Next week, yeah. I know Layla. She's the only lady in the class, so she's always easy to know. Maurice. Yeah, I know Maurice. Yeah, I saw it back there. Leith. I'll get you. I usually know those names around the first. When we go to lab, I will. Newell. Okay. I know Damien. I know Wigginton. And Willingham. Okay. So everybody's here but Layla today. Yeah, we have one coming up this spring here. Amazon is supposed to have, but I don't know the date. I saw it on the news, and that's the only thing I know about it. They said they're going to have it here at the Lawson, but they didn't. And then we have one in the spring. In fact, they sent out an email. I had to find that. I don't think they had the date, and I don't think it's on the calendar. We have ours down at the Bessemer Civic Center, but Amazon is supposed to have one here. Let me send it. Let me see if Nancy knows. What happened to my email? Oh my goodness. Their syllabus agreement, right? It was due today. Into the new Blackboard? Okay. Really? What do y'all think about the new Blackboard so far? It's unfortunately, it'll make a difference whether you like it or hate it. It's here, right? It is, and we try to set ours up a lot like the old site. So hopefully, so everybody okay on the relays? Y'all understand relays, right? So relay has two types of contacts, and these would be the contacts. These would be drawn like this. These are normally open. So that means if the relay is not energized, which is a term we're going to use a lot. So if we energize it, then the solenoid moves and changes the position of contacts. So what this symbol means is that if I came over here, this was L1, and then I had this was controlled by a relay, and then I had a light over here. Then the position it's in right now, this contact would be closed and the light would be off. I come over here and put power on the solenoid. It causes these things to shift. So this would move down here. My circuit would be wired between here and here, right? You'll understand that. So now the contact's closed and the light will come on. And these are called normally open contacts. The symbol for normally closed contact looks like this. It has a line through it. So the normally closed contact, and they don't have it, I don't have it drawn the way it should be. So normally closed contact, while the relay is de-energized, normally closed contact would be like this. Oops, sorry. So power would be down here. So what would happen is that now current could flow. When the relay was de-energized, then current would flow through the contact and go to the load. When we energize it, then this guy here would drop down. It would move right there. And what happens now is it would do what? So whatever was normally closed, the load would be energized, right? When the coil was, the contact would be closed when the coil was de-energized and was open when we energized those. So these relays are going to control two types of contacts, right? Either what? Normally open or normally closed. Everybody understand that? We've already looked at this. . And we basically know the difference between the ladder diagram and a wiring diagram, right? So about the only thing we're going to use the wiring diagram for is the power. We're not going to try to figure out the control circuit inside it gets very complicated. These are very easy, guys. So motor starter, these are relays that have overloads on them. A magnetic motor starter. So we have the manually operated motor starters, manual motor starters, and some of them have overloads on them, some of them don't. I don't know if ours does. I don't know if this little one right here does or not. Let's see if I can find it. That's the selector switch. We got one, guys. What we're passing around is called a manual motor starter. It still has the overloads on, but instead of us controlling it with a relay, it's actually controlled with push buttons. Normally we have one reset button on the overload, which allows us to do what? Reset it if an overload occurs, right? So all the current that goes through the motor runs through the overloads. And the overloads are there to determine if the motor does not start or if it stalls. Because your overcurrent protection devices have to be rated to let the motor start, right? You understand that? And if it lets the motor start and the motor stalls, then your circuit breakers and your fuses are not going to trip out. So we have to have a circuit that detects if the motor does not start, right? We talked about that, right? And these are your overloads. So this is called a magnetic motor starter. Some people just call it a motor starter, but yeah. So we have two types. We have a manual and we have a magnetic. So the magnetic is actually controlled by a relay, and then a manual would be controlled by you, right? So we pick up another symbol. So this right here is the actual sensors that sense the overload. Right here, these hook shaped right here. Now originally we use heaters. So we had a tube, we'll show that, had solder in it. Solder melts at a pretty low temperature. The heater's wrapped around the coils of the solder. There's a spring in there trying to push. And what would happen is when these heaters got hot enough, it would melt the solder. Now the solder turns into liquid. It's no longer solid. Had a spring on there that would trip out. Overloads more and more are moving to solid state overloads. So on a heater overload, if you change motors or if you change currents, you'd have to change the heaters. Solid state overloads, you got a little dial on there that you can turn, which is also in itself dangerous. I don't like it. So what would happen is a motor kicks this overload, and what's the guy going to do? He's going to go to the overload and turn it up. Try to get back in work, right? And then I saw out at U.S. Steel, they would jump over overloads just to keep things running. So because they were being paid incentives, so they got paid by how much they put out, and if something is broke or burnt up, yeah. So the problem with these electronic overloads, they got a little dial on them. You just take a screwdriver and turn them up, and eventually you'll turn them up and you'll burn up your motor, and then you're really down, right? So now instead of replacing defective wire, you're replacing the motor. So this is now the symbol for all types of overloads, whether they're thermal overloads, whether they're heater overloads, whether they're solid state overloads. This shows the sensor that's sensing the current. And these sensors control this contact right there. So it's working kind of like a stop button, right? You understand that? So what happens if it seals itself in, you open it up over here, it breaks the current, the contactor drops out, opens up the seal in, and you cannot start it until these things cool off. So most of the time, it's like a circuit breaker in your house. Normally if you're standing at a circuit breaker, when it pops, you can't reset it, because you got to wait till it does what? Cools off a little bit. So even these are the same way. So normally you would reset it once, and if it comes up and everything's okay, you leave it alone. If you put it back down and it runs for 10 minutes and pops again, you don't tie the overload reset down, right? You understand that? You figure out what's going on, because you could cause fires and you could cause burn up motors. Motors are not cheap. Are we okay? And of course, this would be the pictorial diagram, which now is starting to get more complicated. So that's about all that's in this chapter. Have any questions? Y'all still playing around with the manual starter right here? These things. This is originally, this is a motor. So what you'll find out on a motor starter is that they got a nameplate on them, and usually they give you the horsepower that this thing can run. Now, I don't know if we can pass this around or not, but what you'll notice, the higher the voltage, the bigger horsepower the motor can run. And why is that? So it's normally 740. It's about 746 watts per horsepower. So that's the rule. And of course, over here we're still using horsepower, which is real hard to deal with, because I say a 5 horsepower motor, nobody usually says, well, that's bigger than a 2 horsepower, right? Which makes no sense to a lot of people. The rest of the world is using kVA. They're using watts, how much it pulls. But roughly 1 horsepower is equal to approximately 746 watts. So I is equal to P over V. So if I had a 5 horsepower motor running at 120 volts, that's going to be 5 times 746 running at 120 volts. So what would be my current? What's that? 31 amps. So let's raise this up to 240 volts. What would that be? So that means if my starter was rated at 31 volts, what we just noticed is it dropped down to 15 point something volts, which means now if it's rated at 31 amps, I could run a 10 horsepower motor, because now I'm running at 240 volts. So that's why you'll notice on these magnetic motor starters, the higher the voltage, the higher the horsepower motor you can run, because the contacts are rated at a current, right? You understand? And the higher the voltage, the less current's required to produce that horsepower. That is a very, very important concept to understand, right? You understand? So that's why when you look at this thing at 440 volts, this guy could run 440 volts. He could run a 10 horsepower motor. At 220, he could run a 7.5 horsepower motor. At 110, he could run a 3 horsepower motor on this motor starter right here. And this is a sure enough motor starter, right? Originally, what they did on their overloads, they just put the overloads on L1 and L3. because they realized, they thought, well, if we have an overload on this phase, they'll overload these two. They finally realized that they could still burn stuff up every once in a while on certain situations. So now they have an overload sensor in all three phases. So that's why this got rid of obsolete. You're still going to run into these. Industry has a tendency that if something's doing what it needs to do, they don't do what? They don't replace it just because there's a new version out there. So if you get into a real old plant, like maybe some of the old plants out at US Steel, which most of those are not running anymore, you still might run into these things. Most of them now, thermal overload contactors are a lot cheaper, so you'll see a lot of motor starters out there with thermal overloads. Most of your new installations, brand new, which is part of the installation, they're not buying the parts, when they break. They'll probably use electronic overloads, which causes problems now, because here, if I change the current, I'd have to literally change the heaters, right? You understand that? On an electronic overload, you can do what? Got a little dial on there, you can do what? Change it. I don't know. Yeah, this is an electronic overload. So it's got that little old yellow thing down there. So what happens is that, tendency of men, and I don't know, guys, it's just built into our genes. We'll see a switch and we'll flip it to see what it does. Women will ask you what it's going to do before they flip it. So that's just in our genes. So we got a switch over on the wall over there. It controls a relay. It's an emergency stop, but it's a standard light switch. And it's up, would energize the relay and turn on all the power. And you flip it down, it would turn off the power. We get it home and we couldn't access anything here because the network switch was on that circuit. Because people will come, when guys would come in and they'd say, "What does this do?" Even though it does warning and all this stuff on there. Guess what we did to resolve that? We hung a piece of paper over it. Because we don't need it. It was our building over there was originally automotive, so they had that emergency stop. All we got is electronic stuff. So all we did was just hang a piece of paper off of it. So now guys can't watch. They don't see it, so they don't flip it. That's a true story. Yeah, it would happen all the time. We'd get it home and couldn't access it because the network switch was turned off. We'd come in and somebody had hit that switch to see what it does. What time does this class get out? I got to get back in sync, guys. What's that? Okay. So about with an hour and a half left, we're going to try to do our first lab. And what it is, it's just an inventory lab. And of course, the inventory lab,